section 6.5, the kernel and the range of linear transformation. You have to check the slides before you were watching this video. So let's start with the first example. It's telling you let T be a linear transformation from P2 to R squared. Be a linear transformation defined by transformation of any polynomial with second degree to A minus B, B plus C. They ask you which of the following polynomial is going to be in the kernel T. So let's check that. What I'm going to do here, I'm going to solve it. I'm going to find the kernel. So here's the transformation. Let A plus BX plus CX squared is polynomial be a vector in P2. The transformation of this polynomial is going to be equal 0 because we need to find the kernel, and the kernel is take any polynomial from P2 to the 0. That means the range for this polynomial is going to be only 0. That's what it means finding the kernel. The transformation of the polynomial is going to be A minus B, B plus C equals 0. That means I'm going to solve these two equations, A minus B equals 0 and B plus C equals 0. So A is going to be equal B and C is going to be equal negative B. Let's B equal T. Before that, that means our kernel for the T is going to be all the vectors in P2 such that A equal B and C equal negative B. If you let B equal T, so it's going to be A equal T, C equal negative T, and B equal T, because we assume that. So the kernel T is going to be T plus Tx minus Tx squared. If you let T equal 1, you're going to get this polynomial, which is belong to this kernel. If you let T equal 2, you're going to get this polynomial from P2, and it's belong to the kernel. Let's check that. That means the transformation for this polynomial is supposed to be equal 0. That's why it's belong to the kernel. So if you take T to this polynomial, which is 2 plus 2x minus 2x squared, is going to be equal. I think I did that here. Transformation for this polynomial is going to be 1 minus 1, 1 minus 1, which is equal 0. The transformation for this polynomial also is going to be 0. That means any polynomial with these three conditions, A equal T, C equal negative T, and B equal T, which is these two conditions, that means the kernel is going to be, or this one is going to be, belong to the kernel. That means the transformation for this polynomial is going to be equal 0. So that means if you look to A, which is this one, it's belong to the kernel. Before I'm going to B, because B is below, like we need to find the range. Let's see the kernel of T is going to be, that's what we found here. That's mean this one is the kernel. This is our kernel, which is T, wait a minute, no, this one, T plus Tx minus Tx squared. Now let's go ahead and find the range. Now the range is going to be each vector W belong to R2. There exists a vector, which is a polynomial, in P2 such that the transformation for this polynomial is going to be equal W. So we're going to assume that W, because it's R2, so we're going to assume that C and A in R2, such that the transformation for any polynomial in P2 is going to be CA. Now, the transformation for this polynomial is going to be A minus B, B plus C equal to the C and A. Then we need to solve this system. So A minus B equals C, B plus C equal A. Cancel the negative B and B. So we're going to get A plus C equals C plus A. So here's the range. That means the range, any any vector belong to R2 with this condition. If you add A plus C, it's going to be the same thing, C plus A. Choose this vector, 1, 2. 1 plus 2 is the same thing, 2 plus 1. 5, 6. 5 plus 6 equals 6 plus 5. So that means we have more than one vector, which is all R2. So that's our range. So our range is going to be all R2. So our range, you see, here's our R2. Now let's go to, they're telling you which of these vectors is going to be belong to the range. Just let's satisfy this condition. The condition is going A plus C equals C plus A. So the first one, 0 plus 1 equal 1 plus 0. The same thing with the second one. The same thing with the third one. That means I can choose this one, and this one. So that's it for this example. Let's go with the example 2. Example 2. Now let T be a polynomial from P2 to P2, be a linear transformation defined by transformation of P of X equal X P prime to the X. That means the derivative of X. Find the base of kernel and range. So let's see how we're going to solve this one. So one of the definition, it says any transformation from V to W. Nullity, which is going to be the dimension of the kernel. How are you going to find the dimension of the kernel? First of all, you have to find the kernel, and then you're going to find the dimension. The rank of T is the dimension of the range. So this is really important because you're going to get confused. Nullity is the dimension of the kernel. The rank of T is the dimension of the range. So let's work with this example. Our transformation from P2 to P2, T of Px equal X, P prime of X. First of all, I need to find the kernel. So let P of X, which is A plus X squared plus CX squared, A plus BX plus CX squared. The prime for this one, which is the derivative, is going to be, the derivative of constant is going to be 0. The derivative of bx is going to be b. The derivative of cx squared is going to be 2cx. Now, let's find the kernel. The transformation of p of x equals 0. That means the transformation of this polynomial equals 0. Now, let's write down the transformation for this polynomial, which is x, p prime of x equals 0. That means x, p prime, which is this one, equals 0. Now let's distribute the x. It's going to be bx plus c to 2cx squared equals 0. That means our condition is going to be, we're not going to let x equal 0. That means the condition with the constant, it's b plus 2c equals 0. That means b equal negative 2c. So this is the condition to let all the polynomials belong to the kernel. So our kernel T is going to be all vectors in P2, which is polynomial, with this condition b equal negative 2c. So the kernel T is going to be all set of constant number or constant polynomial. So that's our kernel is going to be, because if you apply this condition, let's take an example. If you apply this condition, plug in this one here, because we say b equal negative 2c. So a plus b, which is negative 2c, x plus cx squared. Cx squared. I found there is a mistake here. We can't do that because we need to solve the system for one of these. So that means in this case, b is going to be equal 0 and c is going to be equal 0. Because when you solve this one, bx equals 0. So we're just gonna say here, bx equals 0, that's mean b equals 0, and c 2c x squared equals 0, so c equals 0. In this case, the condition here is going to be b equals 0 and c equals 0. That's why when you plug in b and c here, you're gonna get only the constant polynomial. So the kernel of a t is going to be all the constant polynomial. That's mean if you wanna find a base for it, base for the kernel t is going to be 1. So here we're gonna type kernel is going to be only 1, because they ask you to find the base, find bases. So the base is going to be only 1. And let's go ahead and find the range. So the range, we're going to let W equal A plus BX plus CX squared in P2. That means the transformation, here's our transformation. So there exists a vector V, A plus BX plus CX squared in P2 such that the transformation of V is going to be equal W. The transformation of V equal W, which is the same thing because it's from P2 to P2. The transformation of V, which is going to be X, B plus 2CX, because it's the derivative of the polynomial, which is B plus 2CX, equal A plus BX plus CX. Now distribute the X, so it's going to be BX plus 2CX squared. In this case, A is going to be equal 0, and B is going to be B, 2C is going to be equal C. So in this case, here's our condition, and A is going to be any number. You can put 0, and with these two conditions. That means the base for the range, we can choose the one that we can choose only X, and X squared is going to be a base for the range. Because 1, if you choose 1, any number, that means you can choose a 0, and 0, we can't assume that this is a base for the polynomial with 2. So we can choose, if you choose 1, yes, but we can assume that this is a base for the range. The base only X and X squared. Because you see here, we have only the transformation X and X squared. There is no constant by itself. That means the base for the range is going to be X and X squared. So we're going to choose here X, comma, and X squared. We have to keep going on this example. Now, nullity of a T. The nullity of a T is going to be the dimension of the kernel. The dimension of the kernel is 1. The rank of a T is going to be the dimension of the range, which is going to be 2. So dimension of the range, because we have 2 bases, so it's going to be 2. The dimension of the kernel, we have only 1, because all constant polynomial. So the dimension for this one is going to be only 1. So the nullity of T is going to be 1, and for the rank of T is going to be 2. That's it for the, if you add these together, it's going to be 3, which is the dimension for polynomial 2. This is called the rank theorem. The rank theorem, if you check that in the slides, is 6.19. It says the dimension of V is going to be equal the nullity of T plus rank of T. So if you add the nullity of T, which is 1, plus the rank of T, which is 2, you're going to get 3. And this one is the dimension of polynomial of degree 2. Be careful, the dimension of the polynomial with degree 2, that means the basis. And the basis we can choose for this polynomial is 1. For degree 2 is 1 and X squared. So the basis, the dimension of the basis is a 3. So this is the rank theorem. We're going to use this theorem a lot with the next questions. We got it right. Let's move to number 3. For number 3, they're telling you find either the nullity of the rank. So which one you're going to choose first? Because after that, you can use the rank theorem to find the nullity of the rank. So I always find the kernel. So for number 3, we have transformation from the matrix with 2 times 2 to R2. And here's our transformation, A minus B and C minus D. So kernel of T is going to be all vectors in M times M, such that the transformation of V is going to be 0. Let's assume that a vector, which is a matrix, A, B, C, D. The transformation for this matrix is going to be 0. The transformation for this matrix is going to be A minus B, C minus D equals 0. Let's solve these 2 equations. So A equals C, A equal B, and C equal D. That's mean kernel of T, all vectors in M times, the matrix here is 2 times 2 with dimension 2 times 2. With these 2 conditions, A equal B and C equal D. Kernel of T is going to be look like one of these. And both is going to be right. Because A equal B, that's mean A, C, C, or you can say B, B, and D, D. That's mean the base for this one, for the kernel, is going to be, you can choose only these 2, 1, 1, 0, 0, or 0, 0, 1, 1. So this is the base. The dimension of the base, we have 2, 1, 2. That's mean the nullity of a T is going to be equal dimension of the kernel. The dimension of the kernel, which is equal to. Now, dimension of V, which is all matrices with dimension with 2 times 2, the dimension is 4. Why? Because we have, here is the standard base for the matrices with dimension 2 times 2. So the dimension for the V is going to be equal 4. So by using rank theorem, dimension of V equal nullity of T plus rank. The dimension 4, nullity is 2, and rank equal rank of T. So the rank of T is going to be 4 minus 2, and it's going to be 2. That's mean for this example, the nullity of T is going to be 2, and the rank of T is going to be also 2. Got it right. Let's move to number 4. So for number 4, we have transformation from P2 to R2 with the transformation T of Px equal P of 0 and P of 5. So let's check that. Let P of X a polynomial with degree 2. I'm going to find these 2 conditions. P of 0 is going to be A plus B, because X is 0. So we're going to get P of 0 equal A, and P of 5 is going to be this polynomial. Now, let's find the transformation of P of X equals 0. The transformation of this polynomial equals 0. That's mean here is the transformation P of 0, P of 5. P of 0 is going to be A, P over 5 is going to be this polynomial, which is A plus 5B plus, in fact, this is not polynomial. We can say this is polynomial because B and C are numbers, constants, numbers. So anyway, like we're gonna write down this equals 0. That's mean A equals 0 and everything here equals 0. Let's simplify this one. Divide by 5. So B is going to be equal to negative 5C. In this case, the kernel of a T equal polynomial with these 2 conditions, A equals 0 and B equal negative 5C. So this is the kernel. If you let C equal T, you're going to get A equals 0 and B equal negative 5T. Now, let T any number. If you let T equal 1, you're going to get this polynomial. Here's T, here's polynomial. Let T equal 2, you're going to get different polynomial. If you check for this polynomial, negative 5x plus x to the power 5. The transformation for this polynomial is going to be P of 0. P of 0, plug in 0 here and 0 here is going to be 0, which is belong to the kernel. A plug in 5, negative 5 times 5 is going to be negative 25, a plus 5 squared, which is 25, so it's going to be 0, which is belong to the kernel. So any polynomial, you get t equal any number, you're going to get here, you're going to get a new polynomial, but this polynomial is going to be belong to the kernel. Now the dimension for this one, this is really important. The dimension for this one is going to be 1, because we have only one base to create polynomials. We don't have more than one base. We have only one base to create these polynomials. Every time we need let t equal 1, t equal 2, t equal 3, but we can use exactly the same base. That's why the nullity is going to be dimension to the kernel, which is equal 1. Now, by using the rank theorem, which is 619, the rank of t is going to be dimension of P2, which is a 3, minus the nullity. So the rank is going to be equal to. So here we're going to type nullity of t, which is 1, and the rank is going to be 2. We got it right. Let's move to example 5. We're going to do exactly the same thing for example 5. For example 5, we have from matrices 2 times 2 to the matrices 2 times 2, and the transformation of the A is going to be AB. With the matrix B, which is a fixed matrix, 2, -1, -2, and 1. First of all, they ask you also to find kernel of T, nullity of T, and rank of T. So I'm going to let A equal A, B, C, D. The transformation of A equals 0. This is to find the kernel. The transformation for this matrix equals 0. The transformation for this matrix is going to be this matrix times the fixed matrix B. We're going to get 2A. We're going to multiply the first row times the first column. And the first row times the first column, and the first row times the second column. Then the second row times the first column, the second row times the second column. We're going to get this matrix. I'm going to take the 2 as a common from here. Take the negative sign from these 2 and the 2. We're going to get, if you solve this one, or this one, or this one, or this one, is going to be the same. I'm going to take this side, negative sign. That's mean solve this one. So A is going to be equal to B and C equal D. If you solve these 2, the same thing, you get A equal B and C equal D. That means kernel of T, all matrices with these 2 conditions. A equal A, C equal C, B equal B, and D equal D. So both is going to be right. The base for this one, 1, 1, 0, 0. 0, 0, and 1, 1. That's mean the dimension for the kernel is going to be 2, which is the nullity. The nullity is the dimension of the kernel, which is equal to. By using the rank theorem, which is 6.19, so the rank is going to be dimension of a V, which is 4, minus the nullity 2, so it's going to be equal to. That means the kernel of T is going to be, we need to write down the kernel of T, which is as a matrices. So I'm going to write down this as a matrices. So 2 bracket, I'm going to say 1, 1, close the bracket, comma, another 2 bracket, which is 0, 0. I'm going to close this one. Then I'll have to close the bracket, comma, and the other matrices is going to be 0, 0, and 1, 1. So this is the kernel of T, the nullity, and the rank is 2 and 2. We got right. Let's move to next example. Example 6. Consider the following linear transformation, and from R2 to R2 defined by t to the xy equal 3x minus y and x plus 3y. Find the nullity of t. So let's check how we're going to solve this one. We're going to find the kernel first. So the transformation, and here's t of xy equals 0. Here's the transformation equals 0. That means we have these equations. Let's multiply the first one by 3. We're going to get 10x equals 0. That means x equals 0 and y equals 0. So the kernel of a t is going to be all points in R2 or vectors in R2 with x equals 0 and y equals 0. So that means our kernel is going to be equal 0. So that's really important. If its kernel equals 0, that means the dimension of the nullity, the dimension of the kernel is going to be 0, which means the nullity for this one is going to be equal 0. So this is the first part of this question. The nullity is going to be 0. Now, if you look to the second part, determine if the linear transformation is 1-to-1. So that's the definition of how to find or prove that the transformation is 1-to-1. The transformation of x1, y1, x2, y2 is going to be here. And in this case, the first one is going to be equal the first row, and the second row here equal the second row. You get two equations. If you solve these two, you're gonna get x1 equal x2 and y1 equal y2. That means the transformation is 1-to-1. There's another thing to prove that this linear transformation is 1-to-1. If you check theorem 620, theorem 620, it says if the kernel, here is 620, a linear transformation is 1-to-1 if and only if the kernel of a t equals 0. So by this theorem, by 620, kernel t equals 0. That means this transformation is 1-to-1. So you can use this definition to prove that it's 1-to-1, or you can use the theorem. That's only if the kernel equals 0. If it's not equals 0, that means this is not 1-to-1 transformation. Now we can choose here just 1-to-1. Now let's check if it's onto. In this case, we have to check that. If you look to the domain and the range, or the codomain, they are exactly the same dimension. That means each vector here, there exists a vector here. That means the transformation for this vector is going to be in the codomain. So since the range in R2, that means each W in R2, which is this one, in R2, that means each W in R2, there exists a V in R2, this one, such that T to the V equal W. In this case, the transformation is onto. So onto, we can choose onto because the domain and codomain have the same dimension. So here, onto, because the domain and the codomain have the same dimension. Okay, so now we're done from this one. Any transformation 1-to-1 and onto is isomorphism. So this is, we're going to take this one also. That's mean when they're telling you this is transformation is isomorphism, that's mean it's 1-to-1 and onto. And if they're telling you prove that this transformation is isomorphism, that means you have to prove that the transformation is 1-to-1 and onto. That's it for example 6. Let's keep going with example 7. We're going to do exactly the same thing with example 7. So for example 7, we have the transformation from P2 to R cubed. And here's our transformation from polynomial to R3, 3a minus b, a plus b minus 4c, and c minus a. So we need to find the nullity and if it's 1-to-1 or not, or onto or not. So let a plus bx plus cx squared in P2, the transformation is going to be 3a minus b, a plus b minus 4c, and c minus a. And then we have this system. I'm just going to switch these two. I'm going to write down, convert the system to matrix with 0, 0, 0 by reduction. We're going to get these two. Here is the new matrix. Then it's going to be a minus c equals 0 and b minus 3c equals 0. That means a equals c and b equals 3c. Let c equal t. So here's our kernel. It's going to be t plus tx plus 3tx squared. If you let t equal 1, you're going to get a polynomial, which is the transformation of this polynomial equal 0. So in this case, the kernel of t not equal 0. That means we have more than one solution, non-trivial solution. So t is not 1-to-1. I did that because theorem 6.20. So they say if the kernel equals 0, that means this is not 1-to-1. So the first thing, nullity of t, which is the dimension of the kernel. The dimension of the kernel, we have only this part. If you let 1, 2, 3, so this is going to be a base to create more than one polynomial. So we have only one base. That means the dimension for the kernel is going to be 1. So the nullity of t is going to be 1. And then write down this nullity, which is the dimension of the kernel, which is equal 1. That means the dimension for the kernel is going to be 1. And it's not 1-to-1 because our kernel not equal 0. And by this theorem, the t is not, the transformation is not 1-to-1. By this theorem, 6.21. Let's check this theorem. What it says. This theorem, it says if you have exactly the same dimension between the dimension of V equal the dimension of W, then the linear transformation is 1-to-1. So if the dimension of V equal dimension of W and the linear transformation is 1-to-1, if and only if it's onto. So you're going to check the dimension. If it's equal and you have 1-to-1, that means it's onto. If it's onto, that means it's 1-to-1. So the dimension of P2 is a 3. Dimension of R3 is a 3. So this condition is satisfied. But the transformation is not 1-to-1. That means is not it's not onto. So it's not 1-to-1. So it's mean not onto. Why? Because not onto because it's not 1-to-1 and the domain are the same dimension, but it's not. So we're going to choose this one. That's it for this example. You got it right. Let's move to number 8. Number 8, we're going to do exactly the same thing like number 4. So they ask you to find the nullity of a t, and they ask you to find if it's 1-to-1 and onto. So here's the transformation, P of 0 and P of 2. We can assume that P of x, here is the polynomial with degree 2. And P of 0, you're going to get this one. P of 2, we're going to get this polynomial. It's exactly like example 4. So the transformation of P of x equals 0. the transformation of this polynomial equals 0. That's mean P of 0, P of L2 equals 0. So we got these two. That's mean we have A equals 0. This is a first condition. And the second condition is going to be equal negative 2C. Let C equal T. So here's the two conditions. That means here's our kernel. So in this case, the kernel of T is not equal to the 0. The dimension of nullity of T, dimension of nullity of T is the nullity is the dimension of the kernel, which is equal 1, because we have only one base to create all these polynomial with these two conditions. By theorem 620, if a kernel not equal to the 0, that means this is not 1-to-1. So the first thing, the dimension of kernel, which is the nullity, is equal 1. And the second thing is it's not 1-to-1 because our kernel is not equal to the 0. So I'm going to choose not 1-to-1. And by theorem 621, they ask you to find the second part, determine if the linear is onto. I did like you can do by using the other thing, because why I did these steps, because I can't use the theorem to 6.21 because the dimension of P2 is a 3, the dimension of R2 is 2. Because theorem 621, they're telling you the first condition you have to get two equal dimensions so I can use the theorem. But the dimension is different, so I can't use theorem 6.21. But check what I did. Nullity is 1. I'm going to find the rank. The rank is going to be dimension of P2, which is a 3, minus nullity, so I get the rank of a T equal 2, which is mean the dimension of the range. So now I have the dimension of the range. Dimension of the range is 2, which is equal the dimension of the codomain. Dimension of the range is equal dimension of the codomain. That's mean this is onto. So this is another way to find if we have different dimension. So I'm going to find the dimension of the range by finding the rank. The rank is going to be the dimension of the range. So that means that our range is 2, which is equal to the R2, which is the codomain. So that means T is onto. So we're going to choose it's onto because the range of T exactly the codomain. So we're going to choose it's onto because of that. We got it right. I told you before, if the transformation is 1-to-1 and onto, that means it's called isomorphic or isomorphism. So let's check example 9. Example 9, we have V equal P2 and P of Lx in P3 equal P with conditions such that P of 0 equals 0. The transformation from P2 to P3. I'm not going to do the first one because you have to check all of these. I checked the second one. I checked. Yes, the second one. And you have to do the same thing for all of these to check which one is going to be the right one, which one is going to be isomorphic, which is mean 1-to-1 and onto. For this one, I checked the second one, and let's see if it's isomorphic or no. So the second one, I'm going to check if it's 1-to-1. By this theorem, here is the transformation. We're going to let in P2, the transformation is going to be equal 0. That means the transformation for this one is going to be here. This one is going to be equal 0. Why? Because this polynomial equals 0 if and only if x equals 0 or a equals 0, b equals 0, and c equals 0. That means our kernel in this case is going to be equal 0. By the theorem 620, if the kernel equals 0, that means the transformation is 1-to-1. So this is the first step, the first part to prove that it's isomorphic. Now, if you look each polynomial here, there exists a polynomial here. Take this one to this polynomial 3. So for each polynomial p of x in P3, there exists polynomial in P2 such that the transformation for this polynomial equal this one. That's me. In this case, this is onto, so V is isomorphic to W. But for this example, you have to prove, check the first one, check the second one, the third one, and check which one is going to be the right option to prove that is isomorphic or no. That's it for this section. You have one more questions. You have to think about that. I'm not going to solve that for you. I need you to practice. But before you watching this video, always check the slides.